Hello everyone, this is a team video presentation about our CPU scheduler. Our scheduler is a round-robin like scheduler backed by a two-level queue. At first, we like to introduce on how the MFQ scheduler works. As you can see, there are 5 rules for the MFQ scheduler. Rule 1 and 2 reveal is a round-robin like scheduler but favor jobs with higher priority. Rule 3 says a job is placed at the topmost queue initially no matter of its priority. Rule 4 is to differentiate CPU-bound jobs with IO-bound jobs. The final rule is used to avoid starvation. Here is how our scheduler works. It first initializes and computes the round-robin quantum as the median burst time of all customers. On each timer tick, do feed new customers in the first level queue, feed the currently playing customer back into the second level queue if he or she used up one quantum. Elevate all customers in the second level queue to the first level queue if the elevation timer timeouts. Start serving the next customer if the machine is idle.
I'd like to first introduce how our customer class is designed. The ID and arrival time fields are travel, but the others was mentioned. Customers only have 2 possible priorities, 0 for high priority and 1 for low priority. The bounce time is the total number of time units the customer declared he or she shared play the machine. The ticket is the number of time units this customer has been served or they scheduled. When ticks equal to the bounce time, the serving to the customer is regarded finished. Here comes the core of our scheduler. The backing two-level queue, Q0 and Q1 are high priority and low priority customers respectively. The reason why we use queue data structure is that a queue is first in, first out, which expectedly reveal the older customer being fed into the schedule. When a new customer arrives, it's fed into the first level queue, no matter of its priority. When a playing customer is suspended due to use up one quantum, it's fed back into the queue. This time, whether feeding into the Q0 or Q1 depends on its priority. This is slightly different with the MLFQ scheduler.
Central parameter of a round-robin-like scheduler is the length of a quantum. If it's too long, the scheduler may suffer from confound effect. If it's too short, the cost of switching would be unacceptable. Although this assignment has no switch cost, but it will increase the waiting time. After a few trials, we choose the median of customer burst times as the base quantum. When the machine is idle, we need to schedule the next customer in the waiting queue. To prefer scheduling high priority customers, we first inspect Q0, and if it's empty, we then inspect Q1. This inspection order will reduce the response time and waiting time for high priority customers. To avoid starvation, the MLFQ scheduler will move all jobs in the lower queues to the topmost queues periodically. On each tick, if we find that the elevation timer timeouts, an elevation is performed to move all customers from Q1 to Q0. Note that the elevation cannot be done too frequently or too lazily. If it's too frequent, there's no difference for high priority customers and low priority customers. If it's too lazy, some low priority customers may be temporarily starved. Our scheduler is very flexible that there are many turnable parameters. By turning these parameters, our scheduler could be applied on various workloads. The benchmark results for our scheduler is shown on this slide. The benchmark results for the other 4 tests have the same pattern of statics. Our design beats the baseline scheduler on longest response and end switches, but lost on total wait. And that's all for our presentation. Thank you.